Yeah, I think now the recording is on, and you should be able to see stuff clearly. Okay, are we good to go? Okay, all right. The first lab is basically your states of matter lab. Okay, and we'll try to understand the different states of the matter. Okay, now let's start. First, when you open the lab, the links for this lab are posted on the website on the Learning Center. Yeah, when you click it, it will open in a new window, and the download start immediately. Allow the download, and when the download is done, move it to a different place, save it in a different folder, and double click it. If you have Java, latest Java installed on your computer, the lab should open now like this. Okay, and they have two tabs: solid, liquid, gas phase. Gas tab, and then we have phase change lab. We're going to use both the tabs. First, we'll start with our solid, liquid, and gas tab. Yeah, so once the lab is open, select from here atoms and molecules, select neon. Okay, there are different atoms and molecules here. So the first lab will select neon, and first thing you should realize is that the atoms or the particles here are atoms. Yeah, it's a single particle. So each round sphere here indicates that is a neon. You can see the color is also blue here. Okay, now set the solid. So once that is done, you set here as a solid. Yes, that is correct. Each round sphere here is an atom. Yeah, and this is a solid. So we make it a solid, so it comes right in the center. You can see that. Yeah, and you can also see that they are vibrating at their positions. Can you see it? They are moving at their positions. Yes, they are vibrating, and when you do the lab, now there is a little lag between me and you. Yeah, so you may not see it as clearly as I do, but when you do the lab, you will see that these particles, each particle is vibrating at its position. Okay, now you can see that they have little spaces in between them, and that space, in that space they are basically vibrating. Okay, now can you, so we'll come back to this again at the end of the lab. Then once you observe that this is solid, observe the temperature here. Okay, can you note down the temperature? Write it down on a piece of paper, what the temperature of the solid state. Yeah, this is a solid state of neon. Note down the temperature. Now this is a very, very low temperature, remember that. Yeah, do you know in degrees how much that would be? My 13K is how much degrees? Anybody? You don't have to calculate, 273 Kelvin. Yes, exactly, minus 260 degrees. Yeah, so you can see that this is a very low temperature. It doesn't have to be that low, but if you really want to see solid, neon is naturally neon is a gas at room temperature. Okay, so you are condensing it, basically you're making a solid out of it, so to lower the temperature, and so at very low temperature it will be a gas. Okay, I don't know exactly at what temperature it turns to a solid, but let's assume that it's very low. Okay, now now what do we do? Now we turn it into a liquid. Okay, yeah, so now we saw the solid. Now let's say it's a liquid. You can see the particles have now separated even more. Yeah, there are more spaces, and not only they are vibrating, they are slightly moving. Yeah, some of them are actually even escaping. Yeah, some of them are moving out from the bulk of the molecule. This is evaporation. Yeah, so they vibrate even more than they were vibrating in solid. Yeah, temperature has increased at this stage. Yeah. What can you say about the volume of liquid in this case? Is it less than solid or it is more than solid? It is greater than solid, correct? Yeah. So there is definitely more kinetic energy here, can you say, than solid state. Yeah, solid, they were vibrating, so you can say they had some kinetic energy. In liquid state it had more kinetic energy. Yeah, in solid state lower kinetic energy corresponded to lower temperature. In liquid state higher kinetic energy corresponded to higher temperature. What do you expect when you convert this into gas? What do you expect? You should expect higher kinetic energy, higher temperature. Is that reasonable? Volume will also increase. That is a very good observation, Sahil. Yes, that is a very good assumption. Yeah, and let's see if that is the case. Yes, voila, you are right. Yeah, they are now moving. Their area of movement is much larger now. Yeah, they are occupying the entire volume of the container. Yeah, what can you say about the volume of the gas? It doesn't really have a volume, but it occupies the entire space. Whatever the size of the container, if you had, let's say, a larger container, it would occupy a larger space. If you have the smaller container, the volume would be lower. Yeah, so they don't really have a specific volume as you saw in solid. Yeah, liquid, they had a specific volume, but not gas. Gases do not have a specific volume. Okay, but we talk about the volume. Exactly. Yeah, so we talk about the volume. We talk about basically what we talk about the volume of the container. But when you talk about volume of the gas, you talk about the volume at atmospheric pressure of the gas. Yeah, so we'll talk about those later, okay, when we go to next class. Yeah, now you can see that they have higher kinetic energy, correct, and higher temperature. Are we clear on that? What can you say about the density? Do you think the density increased for the gas than solid and liquid, or decreased? Density decreased, yes, because again we have same amount of mass occupying a much larger volume, and obviously so the density should have decreased. Yeah, and that is the case. So gases have very low density. Remember that slide from the class we had, correct? We had that slide from the class, the densities of the solid, liquid and gases, and saw that the gases had very low density. Yeah, and that is the reason behind it. Okay. Okay, so similarly you can also move now to change the phase to water. Atoms and molecules, set it as solid. So this is, you can see the water, okay, and you can see that the water particles are moving. Now each particle is made up of 3 atoms, yeah, 1 oxygen and 2 hydrogens. You can see it right here, and they are vibrating. Yeah, this is ice. This is the structure of ice. Now look what happens when you convert this. Look what happens to the volume. Look what happens to the temperature. Okay, observe 2 things. So when you convert the ice into liquid, yeah, and this is our water, what do you see? The temperature increased clearly. Yeah, the particles are now vibrating even faster. Now they have actually 2 types of rotations. Yeah, in solid they had vibrational energies, correct? They only had vibrational energies. Now in liquid they have vibrational as well as rotational energy, correct? They are rotating. Some of the molecules are even rotating. No, they don't. Yeah, but they have vibrational energies, yeah, and rotational energy, because some of the molecules are rotating. Some of the molecules are escaping, that is evaporation. What happened to the volume? Did it increase or decrease? Sahil, the energies we're talking about is basically how the molecules are vibrating, which fashion they are vibrating. Yeah, so energies, you'll learn more about that in your physics class. But energies, when you vibrate, the energy that is possessed by the molecule is called as vibrational energy. When the molecules rotate, the energy is called as rotational energy. Okay, but you don't have to know that. Basically know that there are two types of motion in the molecule. They are vibrating and they are rotating. Yeah, the reason I brought energy in the equation, because we are talking about temperature. Yeah, so obviously the temperature increased because the vibrational and rotational energy increased. Yeah, in solid case they didn't had any rotation, they only had vibration. Yeah, now you add vibrational as well as, or increased vibrational as well as rotational energy, obviously that energy translates to higher temperature. Yeah, so the question is, what happened to the volume? Increased or decreased? Here again, let me go back to the solid. Yeah, let me go back to the solid and then to liquid. That solid, try to imagine up to the level at which it is filling the flask. Yeah, this is a rough estimate. So this is the area it is, and this is the area it is in liquid state. To me it looks like the volume decreased. Okay, let's do that again. Solid, yeah, it seems like it has a larger space, and you can see that the molecules are actually farther apart from each other. Yeah, there is more space between the molecules in solid state. Yeah, and if you turn to the liquid, the space decreases. Obviously that should also you're gonna have to refresh, Abhishek, I guess. Sahil, is your screen stuck too, or can you see? Abhishek, I think it's your screen only, so you're gonna have to refresh. Okay, all right. So Sahil, doesn't it look like it has lesser volume now? Yeah, so that is the case. I mean, why do ice float on water? Why does ice float on water? Because ice has lower density, because ice has more volume. Okay, all right, Abhishek, is it working now? Yes. Okay, so what we are saying is ice has more volume than liquid water, correct? So which has a lower density, ice or liquid? Ice has a lower density. No, Sahil, yes, Abhishek, ice has a lower density because it assumes more volume, correct? And that is the reason why ice floats on the water, correct? That is the explanation. It's one of the few solids in which actually the density of the solid is higher than in the liquid state. Okay, and let's take it to the gas now, and you can see that again it fills the entire container. The temperature has increased, and now there are basically two types of motions now. Yeah, they are not vibrating anymore, you can see that, but they are rotating and they are moving. Yeah, so they have rotational energy and they have translational energy, correct? Or you can say they have rotational motion and they have translational motion. Okay, and that translates to a higher temperature. Okay, so that is the case. You can experiment with different elements here, but you'll see the same result. Yeah, now what we saw with the neon, let's take solid state of neon. Yeah, and then solid state of, you see the temperature is different for both. Now let's take liquid for water and liquid for neon. The temperature is different. Again, gas state for neon and gas state for water, the temperature is different for each of these, but they behave in pretty much the same way, each of the state, correct? Some difference, like how water has, solid has a higher volume, but the gaseous state for each of the gases, or any gas basically, behaves the same way. They fill the volume, whatever it is, and they behave, and they bombard, they collide with each other, they collide with the wall of the container. Yeah, that's basically the gas behavior. Yeah, okay, so that's lab 1. Now let's go and do the lab 2. Temperatures are different because the materials are different. Yeah, they have different energies. Remember, each molecule has a different energy, different binding energy. Yeah, so if you're converting from solid to liquid, they have different binding energy, and obviously the potential and the kinetic energy would be different. Yeah, and so you learn much more about that in future chemistry classes. So let's not dwell on that right now. Okay. All right. So let's start our second lab. Second lab, we're gonna do phase transition. Okay, this is pretty much the same arrangement. Yes, temperature has to be increased to so if you look at here, let's go back to the same class. Now neon is a gas at room temperature, yeah, because the binding forces are very weak, and so that forces can be overcome even at room temperature, right? Water is a liquid at room temperature because the binding forces cannot be overcome at room temperature. Yeah, maybe a little, but not all. So that's basically, learn about this stuff. So here water is liquid in room temperature. Yeah, so we'll learn about this in much more detail later. Okay, why there are binding forces, what type of binding forces are there, so on and so forth. But you need to realize that even in the solid, liquid and gas state, the molecules have some energy, some rotation, some moment. Okay, they are not fixed. Okay, now let's look at the phase transition lab. Okay, again we start the same way. This is slightly more elaborate lab. Here you have a container in the same way. Here you can reduce the volume of the container. You can see, you can bring down the finger. Yeah, you can push the top lid of the container, so you can reduce the volume of the container. There is a pressure gauge. You can see the pressure of the container. You can put more particles in it if you want to. Yeah, if you want, you can increase the number of particles in the container. We're not going to do that. We're going to stick with the basic stuff. So reset it all. Yeah, start the phase change, select neon again. Yeah, now first thing you do is it's a state diagram. Now here you can see that there is no buttons to change the state from solid, liquid to gas. Okay, and if you want to do that, you're gonna have to increase the temperature here. Yeah, if you want to convert this solid into liquid and to gas, you're gonna have to increase the temperature to do that. Yeah, so notice the starting temperature is 13 K, pressure is 0 atm in this container for the pressure for the liquid, sorry, for the solid. Yeah, can you note that down? Solid has a temperature of 13 K and 0 atm pressure. Okay, now we're going to increase the temperature and see what happens. Okay, can you see that the particles are moving much faster now as you increase the temperature? Yeah, now it is turning into liquid. Yeah, so as you increase the temperature, their kinetic energy increases. Yeah, they are moving much faster. That is the kinetic energy, and as a result of that, some of the bonds between the solid particles would start to break. Yeah, as you keep on increasing the temperature, the particles would vibrate even faster, yeah, and eventually at a right temperature it will turn into a liquid state. Yeah, so that's basically kind of like the liquid state. If you keep on increasing the temperature, let's increase the temperature to a little bit more. Watch what happens with the vibration. Okay, three things you need to watch: vibration of the particles, how fast they are vibrating, temperature, and pressure. Yeah, so again, this is liquid state. Yeah, had very low pressure. Yeah, and as you increase the temperature, now it is vibrating even faster, going to increase the temperature, and it should turn into gas. And what happens to the pressure? Yeah, so I probably increased it a little too much, I guess. Okay, so you basically increase the temperature until you have converted it into gaseous state. Yeah, so there are no clumps like this. It should be like all the particles should be free. So you can see that the pressure is increasing. Now why the pressure is increasing? What is the cause of increase in pressure? Yeah, but this is the pressure in the container, right? So why the pressure is increasing? What is causing? Yes, exactly, Sahil, very good. Yeah, the molecules of the gas here, the neon gas or the particles, are actually hitting the containers of the walls of the container, and that is causing the increase in the pressure. Yeah, now as the temperature, so you can see that it's fluctuating, it's going up and down, because the behavior of the particles is not very ideal. Sometimes it comes close down, sometimes they are up there, so on and so forth. Yeah, there is a fluctuation maybe in the kinetic and potential energy. Yeah, is that clear? What causes the rise in pressure? So let me connect the charger of my laptop. Yeah, okay, here we go. Okay, so now we do the same experiment basically, and change it into water. Okay, and reset, change it, sorry, yeah, first you need to do reset and then change it into water. You can see that the particles are vibrating. Yeah, and you increase the temperature, heat it, you can see that it is now turned into liquid. Pressure is still not increased. Yeah, still zero pressure, it has completely turned into liquid. And now if you start to heat it even more at certain temperature, it will become gas or water vapor as we know, and you can see that the pressure is increasing. Okay, so the pressure is caused by the particles hitting the wall of the container. The harder they hit, the higher the pressure. Now the more temperature you increase, what is going to happen? The pressure is going to increase. The number of particles are the same in the container, correct? But the pressure is still increasing. Why? Because the particles are hitting the wall with higher kinetic energy. Is that understood? What causes the increase in pressure? So you can see that the particles are moving now very fast. Yeah, they are spinning, they are colliding with each other, and they are hitting the walls of the container with increased intensity, and that is causing rise in pressure. Okay. So, all right, so now let's do our third lab, yeah, which we basically did it just now, but we'll do it one more time. What causes pressure lab, yeah. Okay, so we use water molecule. This is still solid. Alright, so basically when it is a solid, we know that the temperature is low, yeah, and the pressure is 0, yeah. Why the pressure is 0? Because there are no solid particles that are hitting the wall of the container, correct? Yeah. Now if you increase the temperature, it turned into liquid. Still very few particles are hitting the wall of the container, which is causing no rise in pressure. Temperature has increased, but the pressure is still the same. Yeah. The particles itself are moving faster. What type of energy, what type of motion these particles have? Can you tell me? There are three types of basic types of motion. Yeah, there is a vibrational motion, there is a rotational motion, and there is a translational motion, which is basically particles moving around. So there is, yeah, forget about these one or two particles that are moving around. Yeah, these are not important. This is the bulk that causes how, Sahil? This is not hitting the wall. Yeah, this is basically at the bottom of the container lying. Yeah, it's not filling the container. The pressure gauge is somewhere here. Yeah, if it's not gonna hit that pressure gauge, it's not gonna read the pressure, correct? Yeah. So now, so what type of motion it has? It has rotational motion and it has vibrational motion, correct? It does not have translational motion. Understood? Yeah. Now increase the energy, and what you see is, okay, let's go back to liquid state again. Sahil is asking me to explain it. So I'm lowering the temperature. You can see that the pressure is decreasing. Yeah, it has become a solid now. So I'll just increase a little bit of temperature here. Yeah, so now it is a liquid. In solid state, there is only vibrational motion, correct? Now as you increase the temperature, what happens? Now the vibrational energy has increased, and the particles now also have rotational motion. Yeah, correct? Now as you increase the temperature even more, now the vibrational motion is not there because the particles are free to move. Yeah, so the vibration can only happen if there are no space to move, correct? So there is no vibrational motion, but there is rotational motion. Yeah, the particles are rotating, and there is translational motion. Yeah, the particles are moving freely from one place to other place. So there are again only two types of motion, rotational and translational. So can you tell me which motion causes pressure? Which of these three motions causes pressure? Vibrational motion is not there, Sahil, because the particles are free, right? If the particles are free, that means they can move. Vibrational motion is caused by because particles are unable to move. They have energy They want to move but they can't because they are stuck in a position, correct? And that's why they vibrate, or they seem to vibrate. But if you free them, obviously they're going to have a translational motion. That vibrational motion converts itself into translational motion. Now they are moving, so they don't need to vibrate. Okay, Abhishek, that is correct. Sahil, you did not answer. What causes pressure? Which of the three motion causes pressure? Yes, translational motion, because we saw when it was ice. Yeah, so let's cool down, make some ice. Yeah, so this is ice. It has vibrational motion. Yeah, the pressure would drop to 0 eventually. This is not decreasing, but the pressure would drop to 0. Yeah. Yeah, that is a quick way to make ice. That is correct, Abhishek. Yeah, very funny. And so the pressure would be 0, because vibrational motion does not cause pressure. Yeah, because because the particles are vibrating, they're at their own position, they are not colliding with the walls of the container, and so the pressure is 0. Now increase the temperature. Now you have vibrational motion, you have rotational motion, but the principle is same. The particles are not colliding with the wall of the motion. You need translational motion for that to happen, correct? And so if you increase the temperature even more, now you get translational motion, and because of the translational motion, the particles hit the wall of the container, and that would cause pressure, correct? Now can you see that the pressure is directly related to temperature? Yeah, as you increase the temperature of the gas, pressure increases. Yeah, and have you understood why? Because the particles would move much faster. The energy of the particle is directly related to the temperature at which it is. Okay, and the temperature is directly related to pressure. Yeah, so the more energy you provide to the particle, the faster they would move, the higher would be the temperature, and the higher would be the pressure. Yes. Okay, so that being said, okay, so that's the end of our third lab. Let me see the fourth lab. Yeah, I'll pull out the notes. Hold on a second. Okay, so let's go back to our solid, liquid and gas tab. Yeah, reset all. Use water as the molecule. Yeah, give me 1 second. Yeah, okay, here is what I did actually. I think when I did the first lab here, I incorporated the fourth lab in it. Yeah, but it is essentially the same idea that we have discussed before, that as you increase the temperature, the temperature increase, as you increase the temperature, as you increase the heat, the moment of the particles increases, and obviously the temperature increases, and consequence of that pressure increases. Yeah, but in this one there is no pressure, so it becomes very simple to understand. Yeah, so let's move on to another lab 5, where we talk about gas properties. Yeah, now we saw some of the laws in our class. If you guys remember, Boyle's law, Charles law and Amundsen's law, and we also saw ideal gas laws. Yeah, and we'll try to understand these laws using the same experiment. Yeah, so now we're going to use a different experiment for this. This is a gas property experiment. Do you guys see this, a different experiment on your screen? Okay. Now basically what we do, we first, so when you open the lab, yeah, there is a container, okay, and you have a handle. You can move the man basically, so the idea is that this person is pushing the handle to the left or back, and that would give you, that could increase the volume or decrease the volume of the container. Yeah, so this is a movable container. Yeah, there is a temperature here, there is a pressure, yeah, there is a heat. You can add and remove the heat from here, and there is a pump here. We are not going to use it, but if you pump it, you can put gas particles in there. Yeah, you can choose what kind of particles you want, and you can pump gas particles in it. It's kind of not very intuitive. I've worked with it, but it doesn't really tell you how much particles you're gonna get in there, so we're not going to use that. To insert the particles, we basically, let's say we want 100 particles in the chamber. We enter 100 in there into this heavy species, and then hit enter, and 100 particles will go in there. Yeah, if we want to increase, if you want to insert 100 more particles in there, you simply change the number to 200 and hit enter. Now there are total 200 particles in the chamber. If you want 50 more particles, you can hit 50, and then just the 50, and then, sorry, I think should be 250. Yeah, so now you're gonna have 250 particles in the chamber. Okay, you can change the parameters here, constant parameters. Remember that for each of the laws we have a different constant parameter, so you can change it if you want a constant volume, constant temperature, constant pressure, or none. Yeah, is that understood? Yeah, very nice experiment, isn't it? Okay, let's go to the measurement tools. You have different types of measurement tools. The one we're going to use is a ruler. Yeah, we need a scale, and you can drag the scale, so you just hold it and drag it. Yeah, and you place it in such a way that the 10 coincides with the right of the container. All right. Now what we do, we move the man on the right, and again you will see the instructions on the learning center notes. Yeah, so don't worry, but so you move the man so that the line coincides with 6. Okay, and this is basically in nanometer, whatever, doesn't really matter, but you can say that the volume of the container would be 4 liter. If you say 1 centimeter is 1 liter. Yeah, so so there are 1, 2, 3, and 4, so you can say it's 4 whatever it is. The volume of container is 4 liter, meter, whatever you want to say. Okay. Alright, so now we move to constant parameter and change the constant parameter to temperature first. Yeah, now we increase 100 or insert 180 heavy particles into the chamber. Okay, so we have fixed the temperature. Yeah, not at 0, but you'll see. So now the temperature is going to be fixed at 300 Kelvin. Yeah, you can see the pressure is increasing. Yeah, and it will steady up at some point. Yeah, and the volume is also kind of like here. Yeah, it's not moving, but the pressure is increasing. So if you increase more particles, obviously the pressure would increase. Now what you see is that the pressure is kind of stirring up at 1.5. Yeah, 1.5 atm. Okay. Now what should happen if we double the volume of the container? if we double the volume of the container, what do you expect? Pressure would decrease. Can you predict how much? Good, Sahil, Abhishek, both of you are right. Can you predict how much? It will become twice, or it will decrease by half, or decrease to half. Okay, that's correct. Let's see if that is the case. Yeah, so we move the man towards the left, so we just have to double the volume. Yeah, so from 6 we will move it to 2. Okay, so we move it to 2, and here the pressure is decreasing. Have we increased too much? No, yeah, correct. Yeah, the temperature is constant. Yeah, we double the volume. Look what happened to the pressure. From 1.5 it came down to 0.75, around that range. Yeah, pressure is, again, it never stabilizes to one single digit. Yeah, it will always have some so it's half, isn't it? Pressure came down to half. Yes, that is correct. Yeah, so now what happened is that the particles now have larger volume to move around. Yeah, obviously that's gonna decrease the pressure. Do you guys remember which law was that? Pressure is inversely proportional to volume. Do you guys remember which law was that? Abhishek? Yes, that is correct. Boyle's law. Yeah, pressure and volume are inversely proportional. In other words, P1 V1 equal to P2 V2. So if you have, say, another gas, or if you change, so if you take a pressure and volume product, so you have 2 times 0.75, or if you take the product of volume and pressure at this point, and if you take the product of volume and pressure at this point, you will see that both the products are constant. Yeah, so here we have, let's say, volume is 4, yeah, and pressure is 1.5. 4 times 1.5 is how much? 4 liter times 1.5 is 6. Abhishek, it's 6. Yeah, now let's see what happens. This is case 1, and let's see the case 2. We double the volume, pressure, so now the volume is 8, yeah, 8 liters you can say, and the pressure is 0.75. yeah, can you give me the answer? How much is that? It should be 6, correct? 0.75 times 8. Yeah, so P1 V1 is equal to P2 V2 is proved. Yeah, that's the Boyle's law. Okay, now let's look at Amanton's law. Okay, what do you have in Amanton's law? What is the constant parameter? Let's reset. Okay, what is the constant parameter in Amanton's law? Volume, correct? Very good, guys. Okay, so we click on volume, introduce 180 heavy particles. Yeah, it doesn't matter how many particles you introduce, you can introduce as many as you want. Yeah, as far as the chamber can handle that many particles. If you increase too many, actually the lid opens and the particles escape. Yeah, there is a lid here, and so if you move the lid, the particles escape. Yeah, so that can happen at increased pressure. If you increase the pressure too much, the lid will open. Okay, so let's introduce 180 particles here. Okay, so now we have constant volume. Oops, hold on a second. Yeah, sometimes things just don't work. So if you have none, reset, constant volume, 180. Yeah, so you can see that the handle is gone now from here. You cannot change the volume of the container. Okay, you can heat it up. Yeah, you can change the temperature if you and that would basically sometimes change the pressure. Yeah, so you'll see that. So let's say, notice the temperature. How much is pressure? Is 0.9, somewhere around that. Yeah, temperature is 300 K. Now what we do is add heat. Okay, and we move the temperature to about 600 K. What do you think is going to happen as we increase the temperature to 600 K? How much the pressure should be? Pressure increases. Yes, you can see that the particles are moving much faster here. Yeah, you can see that particles are moving much faster as you increase the temperature, and that causes increase in pressure. Volume is constant. Oops, went too far, so you bring it down a little bit. Okay, yeah, sometimes it just doesn't stop on how much you want. Yeah, it's gonna be, you know, plus minus 1 or 2, something like that. Try to bring it as close as you want to the designated number. Yeah, and you can see that the pressure, we increase the temperature twice. Yeah, double the temperature, the pressure also doubled. If the pressure is 0.9 before, now we have pressure as 1.8. yeah, 0.9 times 2 gives you 1.8. Pressure also doubled. Okay, that is your Amanton's law. Correct? Abhishek, understood how the pressure and temperature are related? Now what are the constant parameters? Again, remember, the constant parameter is volume and the number of gas particles. Okay, those are the constant parameters. Now let's reset again. Okay, now change constant parameter to none. This is a little tricky when you do the Charles law. Okay, so first you have to do the constant. What is the constant parameter for Charles law? Pressure. Yes, pressure is the constant parameter, and so we need to see the relationship of volume and temperature. Now we see this, we click this as none. Yes, the constant parameter is none, and we introduce, so you have to first stabilize the pressure and then set the pressure as constant. Yeah, otherwise it just doesn't work. It's a little tricky, so pay attention, and if you have any difficulty, see the recording. Okay, I will put the recording on Learning Center on YouTube. Oops. So let's put 100 particles into the chamber. Okay, so let's wait for pressure to stabilize. Okay, and now we move the handle to number 2 on the scale. Yeah, so we move back and handle to number 2. Okay, you can see that the temperature also changed. Correct? Temperature decreased. We need to adjust the temperature and make it 300, because we don't want temperature to change. Not right now, we're just setting up the experiment. Yeah, we are not started yet, so we need the temperature to be 100 before the experiment 300 before the experiment begins. So it's a little tricky to get it 300. Yeah. Okay. Now with this setting, observe the volume is 8 liters. Okay, let's say this is in 8 liters. The temperature is 300 K and the pressure is 0.5 atm. Yeah, you have to follow these specific steps to come to this point, and now you can start your experiment. Okay, it's a little tricky. Alright, now set the constant parameter to pressure. Okay, now we're gonna start our Charles experiment. We say constant parameter is pressure. Now what we do is we decrease, so now the pressure is not gonna change, not by much. Yes, it will fluctuate, but it will stay at 0.5, 0.45. Yeah. So now we decrease the temperature and see what happens to the volume. Yeah. So we'll decrease the temperature by half. We'll bring it down to 150 K. Okay, so we slowly watch what happens to the volume. Remember, this guy is trying to adjust the pressure. Yeah, he wants to bring the pressure to 0.45. So in order to do that, he has to move to the right. Yeah, see, the volume came back to 6. From 8 it came back to 4, or from number 2 it came back to number 6, which is basically the half of the scale. Correct? Volume decreased to about half. Okay, so temperature, as you increase the temperature, the pressure, the volume increases at constant pressure. As you decrease the temperature, volume decreases at constant pressure. That is your Charles law. Okay. Now, fourth experiment, our ideal gas equation. Set reset, click to none. Okay. The inside, okay, so hold on a second, let me read the instructions properly. This is also a little tricky. Okay, so first you do is you choose the constant parameter as none and move the guy to number 3. Okay, so move the right edge to number 3. Now set the constant parameter to temperature. Okay, then introduce 180 heavy particles into the chamber. Yeah, temperature is fixed now. The only variables are volume. Pressure would change if you change the volume. Yeah, but let's wait and see what the pressure is. Okay, so note what the pressure is. It's around 0.9. Yeah, volume is around 7 liters. Correct? You cannot change the temperature. Okay, now what is the ideal gas equation? Do you guys remember the ideal gas equation? PV equal to nRT, correct? PV equal to nRT. So we have the pressure, we know the pressure, we know the volume, we know the temperature, and we know the N. Yeah, but it doesn't specify, notice the equation, it doesn't specify what type of gas you need. Yeah, N is the number of particles, number of the gas particles, or moles of, it's not number but it indicates number. Yeah, N is the moles, number of moles of gas. Yeah, so in this case we have I don't know, 180 particles, but n means number of moles of gas. Okay, we know what 1 mole is. 1 mole is 6.023 into 10 to the power 23 number of gas particles is 1 mole. Yeah, yes, it is always, n is always the same, it never changes. Yeah, and that's the case with pretty much all the science. Whatever the number you see is always the constant. Yeah, they don't change, otherwise it would just create a large number of confusion. Okay, huge confusion if you keep changing the meaning of the letters. Yeah, so they don't change. Now, can we say if we change the gas to some other gas, we should see the same thing, right? We should see that at this volume the pressure should be exerted, or at this constant temperature, at this volume the pressure should be same for any other gas, correct? Yeah, that's what I'm saying. It doesn't specify what gas it is, just specify the number of the gas particles. That's all it specifies, right? So let's reset again. Yeah, or put this to 0. Okay, pressure come down to 0 now, and put light species. Now these are the heavy species, as you said. Yeah, now we change it to light species. Look what happening. The temperature is constant, 300. Yeah, the volume is still the same, and at the same volume and temperature the pressure is exactly the same as before. What has happened here? This is a light gas, so it is vibrating more. Yeah, and it is colliding with the wall with higher kinetic energy. Yeah, I don't know how that turns into an equation, but they are really moving fast, and as a result of that the gas pressure is the same as heavy gas, correct? Yeah, so it doesn't matter what the gas is. What matters is how many number of gas particles are there. Yes, Abhishek. Okay, we'll wait for Abhishek to come back, and then we'll move on to our next session. Okay, we'll wait for about a minute, I guess, for Abhishek. Okay, Abhishek, I was just waiting for you. So is this clear that it doesn't matter what the gas is? Okay. Is the mole of the gas, that's all it matters. Number of gas particles or moles of the gas particles. So if you're talking about PV equal to nRT, is the moles of the gas particles that matters, not the nature of the gas. Okay. Alright, so I'll stop our lab here and we'll continue with some numericals.